All right, so we're going to talk about cryptography in Caliptra.
Cryptography. Turn your mic on, please.
I thought I did. My mic is on. It's on. I can hear an echo.
Testing, yeah.
Yeah. Do I need to like adjust? I'm good. Okay. All right, cryptography, my favorite topic. So I'm Christopher from Microsoft. This is Jeff, Google. We just wanted to talk a little bit about some of the fun cryptography that's used in Caliptra, as well as exposed by Caliptra to be used by the SOC. We'll talk a little bit about like the identity pieces of the root of trust, as well as measurements, and then also some of the pieces that are used in, exposed as mailbox commands and cryptographic services, and how this all integrates into post-quantum. Did you want to start?
Sure. All right, so it all starts with two secrets in Caliptra. First, there's a UDS, 384 bits wide and 1.x. We bumped up to 512 and 2.x, burned at manufacturing time, and then kept alone, except until you want to end of life the device and zeroize it. Field entropy is not burned at manufacturing time. It is burned in the field, hence the name. 256 bits, burned after manufacturing. The reason for burning it later is so that the device can traverse a risky supply chain without having those secrets burned in, so that an adversary in the middle that extracts the secrets won't get at the field entropy. That only comes in when it reaches its home in the data center. We derive additional secrets off of these secrets, CDIs, using the DICE hierarchy. So using HMAC, counter KTFs, it's all very NIST approved. The fact that we're deriving asymmetric keys off of these is maybe a little bit less formalized right now, but we hope that's going to be straightened up real soon. So from UDS, we derive IDEV ID, fixed manufacturing time, and we stratify this. We then have field entropy derive the next layer, and this is so that when you blow field entropy, you haven't damaged your DICE chain. It still routes back to the manufacturing certificate. So that if you do not decide you don't want to care about whether field entropy was blown or not, you can always just walk back to the manufacturing cert. And then from LDEV ID, we go to FMC alias, which brings in FMC measurements and other configuration values, and then runtime, and then DPE contexts, which provide measurements for other things outside of Caliptra. Each of these keys gets certificates where you can then encode the measurements that contributed to their derivation, which gives you strong cryptographic binding of what device am I talking to, what is its configuration, and what code is it running. To deal with post-quantum, we've elected to create separate certificate chains, not hybridized certificates, but different parallel ones. And if you want a hybrid assurance, you could do a couple of independent attestations using each of these algorithms if you're worried about the strength of MLDSA. Here is a diagram. There is going to be a quiz on this later, so everyone please look closely at it. Just kidding. This you can find in the specification. This kind of just illustrates the different components of the key hierarchy. Measurements. So we have Caliptra's own measurements captured into its own native DICE chain. Then we mentioned DPE that can hold measurements of other components. In Caliptra 2.x, we also have direct visibility into the measurements of firmware that's actually loaded into the MCU, which lets you bootstrap trust that way. And we hold not only DPE context, but also 32 PCRs that are essentially rolling hashes where you can deposit those measurements. Each PCR is 384 bits wide, and there's a mailbox command that lets you get the current value of each of those PCRs signed by the FMC alias key. Here are some use cases, or uses that we've carved out for these different PCRs. So the FMC measurements and ROM configuration is in PCR 0 and 1. You'll notice that some are labeled current and some are labeled cumulative. So if you want a bit more of an easier to digest, what am I currently working with, you could look at the current PCRs. And these get reset every time you hitlessly or runtime update Caliptra. If you want a complete log of every change that ever happened to Caliptra since cold boot, you would look at the cumulative registers, which do not get reset across Halos updates. Over to you.
Yeah. All right, cool. So that was the sort of identity pieces. And then as Caliptra has evolved, so it was initially in 1.x extremely focused just on identity and measurements. So it only really had exposed hardware, that did things like SHA, HMAC, ECDSA, and LMS. And this is only kind of partially available outside of Caliptra core. These were services more or less reserved for Caliptra itself, and a little bit exposed to the SoC to do measurements maybe with its SHA accelerator. 2.0 built that out and expanded it so that there's a bunch more cryptographic services that Caliptra provides to its SoC and to MCU as well. So notably AES, ECDH were added, as well as MLDSA for post-quantum. And then it expanded access a bit more to the hardware, or to the SoC. I'll discuss how we did that. And then 2.1 adds additional support for, in particular, Shake as a Shake accelerator for part of SHA-3, MLChem, AES DMA, so that you can use AES in a little bit more performant manner, as well as OCP lock, which we've talked a lot about. The way we've now exposed that in 2.0 going forward is through a system called the Cryptographic mailbox. So this allows you to use Caliptra core as a cryptographic accelerator, and it provides a relatively orthogonal set of APIs that can be used over its mailbox to do cryptographic operations. So it allows either MCU or the SoC or both to use these services, generate keys, use cryptography, and use all these nice hardware engines that we're paying the silicon price for, so we might as well expose them as long as we can do so in a safe manner. This also allows additional services to be more easily built by a companion like the MCU. So Caliptra core is meant to be very tight and focused, and so won't have an implementation of, say, SPDM or PLDM, which are these much larger protocols, and you wouldn't want those necessarily in a very small ROM and firmware. So but in order to implement those, you need a lot more stuff. Like you need AES and you need key exchange and whatnot. So that's where the cryptographic mailbox comes in. I'm going to come back to this slide. So the first question you should always ask whenever you have any sort of new cryptographic services is, how are the keys managed? So that's great and all. How do keys get in? How do keys get out? What's the key story? Because Caliptra has its own keys, certainly, but how am I going to use keys with Caliptra? So Caliptra, fundamentally has very minimal storage and no real persistent storage. So it's not going to necessarily store keys for you, but what it does is it has the ability to essentially not quite wrap keys, but generate keys or import keys and provide them in a wrapped form that you then provide later. And that's sort of the heart of the mailbox system. So are these CMKs, these cryptographic mailbox keys. It's a 128 bytes or 1024 bits of encrypted, basically, blob that you get back from Caliptra, and then you pass to Caliptra to use, and that holds your key material with it. So this way, Caliptra doesn't have to keep all this key material in it, but it can just generate it, wrap it, and send it back. And you provide it, you being the MCU or the SoC, can provide that blob back in to be used. But without requiring Caliptra storing anything. It's not true it doesn't store anything. I guess it does store limited usage information for specifically AES GCM. There, I think we mentioned earlier, there's this 2 to the 32, 4 gigabyte-ish limit whenever you're doing anything with AES GCM, which is an annoyingly small amount of usage. And so we do try to keep track of how much each AES GCM key is used, just so that we don't hit that limit, because keeping track of that is required for FIPS. But other than that limited storage space for those usage counters, we don't store anything in Caliptra. It's all just exported to the user, who is then going to use those mailbox commands. And yeah, like I said, the CMKs have to be used every time. Internally, this is all done with AES GCM to wrap this key material. And it looks sort of like this. The left-hand side is the unencrypted structure. So this just has usage information, making sure you're not using a CMK for a usage it's not meant for, making sure we understand the size, if there is a size difference, if there is a usage counter, that's also kept there and tracked, and things like that, and as well as some other metadata. And then there's also the encrypted blob format, which has enough information, more or less, just so that the cryptographic mailbox system can decrypt that. So now I want to go back to that other slide, which was, again, how do keys get in, how do keys get out? So there's a couple ways to get a key from Caliptra. So Caliptra normally boots up, it's done booting. How do I get a key in? Well, you can import a key. So if you have, say, a durable key stored in fuses or some flash or somewhere, you can import it into the cryptographic mailbox system with an import command, and it will give you back a wrapped key that can then be used for operations. There's also a derive functionality. This allows you to derive additional keys off of the IDEV and LDEV secrets. So if you want a key that's stable across reboot every time, you can say, I want to get a key that's derived off of IDEV, and we allow those to then be returned as CMKs. And that way you don't get the same CMK every time, but you get the same inner key material every time. So the CMKs are always ephemeral, and they always get wiped across reboots. But the inner key material will be the same every time. And so you can use it, you can just rederive the same key every time. And then, similarly, you can use that import functionality combined with the random functionality to generate a random key, for instance. So cryptographic mailbox commands, there's some for basically every functionality within Caliptra that's exposed. AES in a bunch of modes, ECDSA, MLDSA, ECDH, SHA is supported in a streaming mode so that you can stream data in, HMAC and HKDF, and then now in 2.1 we're going to have soon MLChem, Shake, and AES DMA commands as well. I wanted to quickly go over some Adams-Rich performance because there's usually two questions with any post-quantum talk is, what's the performance like and what's the space like? Can't really help with the space, but with performance, it was quite surprising to me, at least, that how well it performs. Something like between 5 and 46 times faster for MLDSA, depending on which exact operation, compared to ECDSA. So ECDSA, the baseline was almost 2 milliseconds, but we're talking, 1/5 or 1/50th of that for MLDSA operations. So that's quite encouraging. MLChem has a pretty similar, I think, performance difference. It's even more consistent, though, since the rejection happens at a different stage. So keygen is extremely fast, and encapsulation and decapsulation, the equivalent of those in ECDSA would be ECDH, would be the... Okay, there we go. Sorry about the feedback. So again, there's still a similar, but actually even more, like 50 to 100x performance improvement. The downside is that these have problems with expansion. So whenever we mask them to make them protect against side channel attacks, we typically get a much worse area overhead, something like 6x overhead for MLDSA and MLChem, as opposed to ECDSA, which doesn't have a huge masking overhead. So I think that covers most of it. As always, Caliptra is open source. We're welcome to feedback and talking about anything we want to add or work on for the next versions. We're open to talking. So, thank you.
So if there's any questions, make your way to the mic.
Yeah, I had a quick question. I didn't see it in the roadmap earlier, but I was wondering if there is a plan to increase the ability of Caliptra to handle more measurements, particularly with regard to the stash measurement, primitives, if that's going to be something like in 2.2 would be enhanced?
I think we do have plans on this. So we haven't officially announced that we're doing this, but we've been talking internally about increasing the number of stash measurements allowed now that we have a little bit more memory in 2.0 and 2.1. And so we have, I don't know if we've settled on an exact number. I think the number was something like 8 or 16 initially, and now I think we are going to increase that, but I don't want to make a promise on to how much. But we are aware of that limit, and it's something we're adding more flexibility to in the near future.
Thanks.
It'd be helpful to hear like what your requirements would be.
Right. If you had a, yeah, exactly. So.
Yeah, I'm Jordan. I work on Caliptra too.
I was looking for you earlier.
Yeah,
What are you asking questions for?
I think, no, I don't have a question. I have an answer. Yes, we can increase the limit. I mean, Caliptra does have limited SRAM, so we have to be a little careful about doing that. But yeah, I think my biggest question to you, or to this is not you're not the first person to have asked this, is what's the use case? Just because you can kind of explode the number of measurements you make if, like, if you're making 120 measurements of your SoC, then the question is like, okay, are we doing something wrong? So I just want to make sure that, like, as an industry, we're designing our measurement architectures in a consistent way.
Yeah, I think the limitation we hit very quickly was when we considered we hit this.
You want to use the mic so everyone can hear? Sorry.
Yeah, I mean, we can also, like, I'm happy
take
to
this
talk
offline as
outside if we want to move on.
Yeah. Are there other questions?
Another minute if you want to use your
Yeah.
minute. So
Are there any other quick questions before we wrap up? I unfortunately did not get a chance to talk about all of the other fun cryptography used internally in Caliptra, which I realized during the last few talks, like the lifecycle controller and the fuse controller has a lot of interesting cryptography. There's another shake engine in there, for instance, for tokens. There's all sorts of other fun things going on, but only have so much time. I focused mostly on stuff exposed to users of Caliptra, so, but I'm happy to talk about any of those pieces as well.
all right, thanks a lot, folks. Yeah, great talk.